Hey everyone, today is going to be the last video of the chapter, and we're going to be covering three big theorems that come up over and over again in calculus. The first you've already seen, that's the intermediate value theorem, but it's definitely worth revisiting. Then we're going to talk about two new theorems, which are the extreme value theorem and the mean value theorem. And so we're going to talk about what these theorems say, and then we'll go over some examples, and specifically some examples where they show up on the AP exam, so we can get used to how to recognize these when they appear in a problem. So the first one we're going to talk about is the intermediate value theorem. And again, this one we've already talked about before. So when we think intermediate, right, I see this word, I'm thinking in between. Okay, and here's what the theorem itself says. So the conditions, kind of the if part of our theorem. So the first condition is that f of x is continuous on a closed interval from a to b. Okay, the second condition is that if I take the y values at those endpoints, f of a and f of b, this value in question, which I'm going to call c, has to be in between those two y values. So I'm going to make a note here. These two are the y values at our endpoints. Okay, so if I have those two conditions, then my conclusion, or the then, we can say f of x is guaranteed. So I'm going to run over here. Guaranteed to equal c. So in other words, f of x will equal c at some x value on the interval by IVT. What this is really telling us is that if we're continuous on a closed interval, then our function has to take on every value in between the two endpoint values. So we use this theorem when we're trying to guarantee a specific output for a function. Okay, we also could say we're trying to determine whether a function ever attains a specific output value. So those are the purposes, that's why we use this theorem. So now what we say since f is continuous, and I'm going to add on a closed interval from a to b, and f of a is less than c is less than f of b. I'm going to make a note here. It could also be that the order looks like that. C just has to be between those two values. Then we say f of x equals c for some x value on the interval from a to b by IVT. Now this wording is a little different from what I've used before. If you prefer this, go ahead and use it. This is kind of the wording that Mrs. Vasta uses. When we go through the example, I'll be using the wording that I used when we previously went through this theorem before. But again, either wording is completely appropriate as long as you're stating your conditions and then the outcome of that theorem. All right, so we're going to look at an example of this. Number one, and this is a basic example that we covered before. So now the question is, if my function f of x equals x cubed minus 2, does f of x equal 0 somewhere on the interval from -1 to 3? So again, we're being asked to determine if the function attains this value over an interval. So that's our IVT. So I know the first thing that I have to check is whether or not this function is continuous, which we know it is. The next thing I have to check is if this value 0 falls in between f of -1 and f of 3. So I'm going to do that now. So f of -1, I'm just going to plug that back in. -1 cubed minus 2 is just going to be -1 minus 2, or -3. For f of 3, I'm going to have 3 cubed minus 2, which is 27 minus 2, or 25. So now I can see that 0 does fall in between those two values. So by IVT, I can guarantee that the function takes on the value 0. So here's what I would say. And again, if you want to kind of look at Mrs. Voss's video to look at her the reasoning that she uses, again, I'm fine with that as well. But what I would say is, since it starts off the same, since f of x is continuous on the interval from -1 to 3, and we know that f of 0 falls between f of -1, so f of -1 is less than 0, which is less than f of 3. Okay, those are our ifs. I'm going to say then, by IVT, there exists a value C in the interval from -1 to 3 such that, f of C equals 0. Okay, so again, I have my ifs. It's continuous. I've checked that that value falls between the endpoint values. So I could say then by IVT, I know there's some value C in the interval such that f of C equals 0. Okay, so that's a basic example. Let's look at a question that might be more likely to reflect something that would show up on the AP test, particularly the multiple choice section. Okay, so it says let f be a continuous function. So right off, they're giving us one of our conditions. We know it's continuous, so we know it's okay to go ahead and kind of pursue the intermediate value theorem. So it's a continuous function on the closed interval from -3 to 6. Okay, so I know f of -3 is -1 and f of 6 equals 3, and I'm asked to determine which of the following condition the IVT guarantees. So let's go ahead and take a look. First one says that f of 0 equals 0. Now, I can guarantee that the function is going to take on the value 0 at some point, because if I look, 0 is in between -1 and 3. However, I can't guarantee where that happens. So I'm going to cross this out and I'm going to make a note that I can only guarantee that f of x is equal to 0 at some point in the interval from -1 to 3. I can't guarantee that it happens at 0, so we're going to cross that one out. Now, part B says that f prime of c equals 4/9. So when I see the derivative, I know this is talking about slope. But we know IVT only guarantees a function value, not a slope. So that option's going to be out as well. All right, so C. It says that my values of f of x have to be between -1 and -3 for all x between -3 and 6. So let's think about this. I'm going to sketch just a little graph. We know here that f of -3 is -1 and f of 6 is 3. And we know it's continuous. So it could really do anything it wants in between there. So let's say my graph did this. So obviously, if we look at that, f of x does not fall in between those two values for all x. Now, we can guarantee that all the values between -1 and 3 will be taken on by that function. But we can't guarantee that all the function values will lie in that range. So that one's out. Let's see, now D, f of c equals 1 for at least one c between -3 and 6. So now, since 1 falls in between -1 and 3, this I can guarantee. I don't know where that happens, but I know it happens at some place on that interval. So D, I can guarantee. And then last but not least, it says f of c equals 0 for at least one c between -1 and 3. Now, at first glance, it would seem like that's okay because 0 is between -1 and 3. However, that happens on the interval from -3 to 6. I can't guarantee that the same thing happens on the interval from -1 to 3, so that one would be out. Okay, so that's more likely the type of question you would see about the IVT on the AP exam, kind of more conceptual and testing whether you really understand the conditions and kind of the outcomes of that theorem. All right, so let's move on. All right, one more here. It says the functions f and g are differentiable for all real numbers. Table gives values of the functions and their first derivatives at selected values of x, and then it gives us a formula for h of x. And so here it says explain why there must be a value r for r in between 1 and 3 such that h of r equals -5. So here, as I'm reading the question, I'm going to ask myself, what are they trying to ask me, right? What is the question asking me? And the question is asking why I can guarantee that a function takes on a specific value, which I know has to be IVT. The IVT is what's going to allow me to guarantee that a function takes on a specific value. So again, I'm going to check my conditions. The first thing I knew was that it has to be continuous. So the first thing I noticed is they told me these functions are differentiable. And we know that if a function is differentiable, it must be continuous. So since f and g are continuous and h is just a composition of those functions, I know that h is going to be continuous as well. So I've kind of met that first criteria. So now I have to find the values h of 1 and h of 3, so I can check that this value actually falls in between. So we're going to use our table to do that. So first I'm going to do h of 1. So h of 1 is f of g of 1 minus 6. So I have f g of 1 is 2 minus 6. F of 2 is 9, so 9 minus 6 is equal to 3. So I know h of 1 is equal to 3. I have h of 3 equals f of g of 3 minus 6. Let's see, g of 3 is equal to 4, so f of 4 minus 6. F of 4 is -1 minus 6 equals -7. So far I know that the function is continuous. Now I can show that -5 is between these two values, so we can use IVT to guarantee it takes on this value. So again, now that I've kind of showed my conditions, I need to write my statement. So I would say, since h of x is continuous, and let's see, I have h of 3 is less than -5, which is less than h of 1. Okay, there's my ifs, my conditions. By IVT, there exists a value r. Make sure you can see that. There exists a value r in the interval from 1 to 3 such that h of r equals -5. Okay, so now we're going to move on from IVT and look at a different theorem called the extreme value theorem. All right, so let's look at the extreme value theorem. So when we're thinking extreme values, right, that's just like the extrema we've been looking at when we were looking at our graphs, doing our graph sketching. So we're thinking about our max and min values here. Okay, and so all this theorem says, right, so our conditions or our ifs, okay, is that if f of x is continuous, and we're going to say continuous on a closed interval from a to b, then f of x is guaranteed, to have both a max and a min on that interval. Okay, so we use this theorem when we're trying to guarantee that a function has a max, or we're trying to guarantee the function has a min. Okay, so what we say is since f of x is continuous, and I would really say it's continuous on closed interval from a to b, then f of x is guaranteed to have a max and a min on the interval a, b by the extreme value theorem. Oops, I'm sorry, you can't see that. Let me move that up and give you a chance to get that down. So really straightforward, right? We're just proving we have a max, or guaranteeing that we have a max and a min. And really this comes up most often when we're looking at our functions and we're checking kind of those endpoints for max and min values. So this won't come up a whole lot, but we kind of use it to justify some of the work when we're finding extreme values as part of that graph sketching work. Okay, so now here's an example problem that we have. If f is continuous for all x on the closed interval from a to b, it's differentiable on that open interval. I know f of a equals 3 and f of b equals -7. Which of the following must be false? So we have a lot of information here. We know our function is continuous and it's differentiable. I have f of a equals 3, so I know my endpoint values. It's going to ask which must be false. So let's see. The first one says f of c equals 0 for some c between a and b. So this, again, part A is asking me to guarantee a function takes on a specific value. I know that's IVT. Since 0 is in between -7 and 3, and my function is continuous, that's actually a true statement by IVT. So I'm going to cross that off. That is not going to be false. Okay. Let's see, part B says f of x has a maximum value on the interval from a to b. Again, because we're continuous on that closed interval, the EVT guarantees that we have a max and a min. So that's not going to be false. Okay, this says, let's see, f of x does not have a minimum value. Now this is going to violate EVT. So that is likely going to be our false statement. Let's just double check for part D. So it's f of c equals -2. So it's asking, can we guarantee the function takes on the value -2? Again, because -2 is between -7 and 3, that's guaranteed by the IVT. So the only false statement here is that f of x does not have a minimum, because we know by IVT we're guaranteed to have I think I said IVT. By EVT, we're guaranteed to have a minimum value. And so this note is kind of what I referred to earlier. The extreme value theorem is really only used to remind us to check the endpoints when we're looking for maximum and minimums. So we know those max and mins could happen at interior points on the interval, right? We find those by finding the critical points, but we need to always remember, if we're working on a closed interval, to check those endpoints as well. All right, we've got one more theorem to go. Okay, one more new theorem, and this is going to be our mean value theorem. Okay, and when we think of the mean, I think all of us probably oftentimes think of the average. And that's going to be a key part of this theorem. Okay, so what does this say? So our ifs say, if f of x is continuous, and I say continuous on a closed interval from a to b. And now f of x also has to be differentiable on an open interval from a to b. Then we can prove that there is a value c in the interval from a to b such that f prime of c is equal to f of b minus f of a over b minus a. So what does this really tell us? If we look at the parts, f prime of c, since that's a derivative, I know that is our instantaneous rate of change. Okay. Over here, this is going to be equal to my average rate of change. So what this theorem is telling me that if I have a continuous and differentiable function, then there has to be some point in that interval where the instantaneous rate of change is equal to the average rate of change. We can also think of it as the slope of the tangent has to be the same as the slope of the secant line. Okay, so we use this theorem when we're trying to guarantee that a function has a specific slope. Or when we're trying to locate the place where a function's average rate of change, I'm going to abbreviate there, average rate of change is the same as its instantaneous rate of change. Okay, and so here's how this all comes together. We would say since f of x is continuous on the closed interval a, b, and it's differentiable on the open interval, then by the MVT, there exists a value c in the interval a, b, such that f prime of c, that instantaneous rate of change, is equal to f of b minus f of a over b minus a, or that average rate of change. Okay, so again, we're going to start with just a base level problem using this theorem. There's two here, but I think we'll just do one. And we can always go back and look at the next one if we have questions about this. All right, so it says to find the values of c that satisfy the mean value theorem. So unlike the IVT where we could only guarantee that it happened, we can actually use the mean value theorem to prove where this exactly happens, where the instantaneous rate of change is equal to the average rate of change. So first thing I need to check is my function here. Since this is just a quadratic, I know that it's going to be continuous and differentiable. So I've been sure to check the conditions first of the theorem. So now I need to do the math to find this value to see where this happens. So let's go ahead and do some calculations. The first thing I know is that f prime of x, my derivative, is negative 2x plus 8. So that's going to be one piece of this. Now I actually need to calculate this average rate of change. So I'm just going to draw a line here. So I have actually, if I use my values, f of 6 minus f of 3 over 6 minus 3. And hopefully I can do these calculations without making any errors. So f of 6, let's see, I have the opposite of 6 squared, so negative 36 plus 8 times 6 is 48 minus 17. So negative 36 plus 48 is 12 minus 17 is a negative 5 minus f of 3. Let's see, I have negative 9 plus 24 minus 17. So if I did this right, I should have 15 minus 17 is negative 2. So now I have minus a negative 2 over 6 minus 3 is 3. So now negative 5 plus 2 is negative 3 over 3 is negative 1. So now my f prime of c, I'm just going to replace this x with a c. So I've got negative 2c plus 8, my instantaneous rate of change, and I want to find out where that equals the average rate of change, which is negative 1. So now I've just got a really simple equation that I can solve. So I've got negative 2c. I'm going to subtract 8 from both sides, which is equal to negative 9. So I get c is equal to 9 over 2. Okay, so I've used the outcomes of that mean value theorem to actually find the c value, right? That tells me at 9/2, the slope there is going to be equal to the slope over the point, or over the interval from 3 to 6. And when we're back in class, we'll just do a quick demonstration on Desmos to actually show us visually that that is the case. So I'm going to put a star by that so we remember to kind of come back and do that. Just look at that visual representation to give us maybe a better idea of actually what we're looking at here. All right, so we'll skip number 2 for now. And we've got a few more problems here to go. All right, so let's look at some multiple choice problems here. First one says, in the diagram below, the graphs of 4 functions are drawn over the closed interval from a to b. It asks how many of these functions do not satisfy the conditions of the mean value theorem on the interval from a to b. So first we have to think of what those conditions were. So if we look back, we said the mean value theorem had to be continuous on the interval, and it also had to be differential at every interior point of that interval. So if I go back here, let's see, it looks like here, let me make a note again, the conditions were continuous on the interval from a to b, and then differentiable at every interior point of that interval. So let's see how many do not. And again, it's always really important to make sure you're answering the question they asked. Here it's how many do not satisfy it. So let's see, if I look at the first one, I can see here I've got a jump here at this endpoint. So I'm not going to be continuous. So I'm going to put a little X by that one. That one's not going to work. My second graph, I'm definitely continuous. I can get from A to B without lifting my pen. But here I have a cusp, which I know is going to make me not differentiable at that interior point. So that one's out. Here, let's see. I am continuous, and it almost looks like I wouldn't be differentiable, but this isn't quite that vertical tangent that causes us problems. So this one's actually going to be okay. And then obviously on the last one here, I'm not even continuous because I have this infinite discontinuity that's caused by that vertical asymptote, so that one's out. So I have 3 of those graphs that do not meet the conditions of the mean value theorem. Let's see. I actually, at this point, want to save these last 2 examples for when we come back to class. One, because this has already been a lot, I realize, and you may be at your capacity for taking in this information. And plus, these questions are going to kind of pull together the theorems that we've been working on, so I think it'll be valuable for us to go through and discuss those when we're back as a class. So I hope you all are having or had a great break, and we'll see you when we're back in class.